the Shaw Prize, the reason we are both here in Hong Kong. So was it 2013?
2013. Yeah.
Yes. Do you sort of remember the moment, remember being told you'd won the Shaw Prize? What was that like?
Oh, well, elation. It was, kind of a feeling of you like me, you really, really like me. And in John's case, it was even more funny because it was sent by email. It wasn't a phone call, and his was put in the spam filter. So I received mine. Mine got through.
Yeah.
And by this point, we weren't at the same place anymore. So I was in the UK, and John was at the University of Virginia. And so I just sent him a little message. I said, "See you in Hong Kong." He said, "What?" He had no idea what I was talking about.
Yeah.
And then the congratulations started to come through in his mailbox.
Yeah.
And he thought, I wonder, and he checked his spam filter, and he saw the prize announcement. So, it's something that every scientist fantasizes about, that they're going to win one of these major international prizes, and, it doesn't happen that often. So, it was a marvelous feeling. The idea that all this hard work that you've been doing really has been influential and acknowledged as such. I think there's just no better lift that you can get from your work. So that was a great moment. And then the ceremony itself in Hong Kong was terrific. We were treated like, it's interesting, when I come to Hong Kong, I'm treated like David Beckham. I'm treated like a star football player. It's that sort of, and I think that speaks well, for the culture here.
Yeah.
They hold the scientists in the highest level of public esteem.
Yeah.
And so that's also nice to see. It's nice to experience, of course, but it's nice to see a culture that values that so much.
Let's talk a little bit more then about the work.
Okay.
And I will try not to get too excited as a fellow fluid dynamicist, because I want this to be as understandable for everyone watching as we can make this.
It's actually very simple. So let me tell you what the astrophysical problem. It has an interesting astrophysical side and then a physics fluid side.
Yeah.
And both of which I think are pretty simple to explain. So the astrophysics side is the study of something called an accretion disk. So an accretion disk, accretion refers to the fact that there's material going around in a disk, like planets going around the sun, only in this case it's gas. And eventually it's piling up and it is building, perhaps even creating the object in the center, which is responsible for the gravity, which is keeping the disk there in the first place. So the problem is the following, that the analogy to planets is too good. That is to say, if you just look at the equations that people were working with, the gas should have gone around in orbits exactly as the Earth goes around the sun, and the Earth has been doing that for 4.5 billion years. And it's moved around a bit here and there. We now know more than we thought, but it hasn't disappeared into the sun.
Yeah.
And so the question is, what is it about the gas that makes it spiral in so much more rapidly? So in this case, the orbits themselves wouldn't be circles or ellipses, but things that really kind of spiral into the center. So what's causing that? And the sort of naive things that you might think of, well, there's the gas rubs against itself in a process that the fluid dynamicists call viscosity. And if I have the material on the outside is going a little bit slower than the material on the inside, as the material on the inside passes, it rubs against the molecules are rubbing against one another, and that creates a sort of friction which can dissipate the energy. But when you put in the numbers, it just fails by orders of magnitude. It's nowhere near as powerful a mechanism as you need to account for the observations. And the observations, especially, it was an important problem, I guess, starting in around the 1970s or so, when people were very keen to find evidence for black holes. This was 50 years ago, and today the evidence is overwhelming. We can take pictures of them. But back then they were very elusive, and to try to find anything that you could about a black hole to give evidence that they exist was very much in demand in astrophysics. So what people did was say, well, we can't see black holes, they're black, but we can certainly see the effects they have on their surroundings. And one of the ways that they would manifest themselves is that they would make a surrounding disk very hot in the process of accretion because of the needed friction that would be required for the gas to spiral in. So there was a sense that the gas had to be turbulent. But why it was turbulent, it was interesting. Why it was turbulent was somewhat of a mystery, at least for most people. So, as you know, there's lots of folklore in the fluid dynamics community about what's going to happen. So one of the biggest, I have to watch myself, one of the big, I don't want to say fables, but one of the basic sort of common wisdom would be that if you have what people call a high Reynolds number fluid, you have a lot of shear, and you have some viscosity, but just a little bit, then that will naturally be an unstable situation. If not in the sort of the linear regime, then in the nonlinear regime, if you take into account finite amplitudes for your disturbances. And so this was a process that had been studied in the laboratory by Osborne Reynolds back in the 19th century. And flow in pipes, in fact, does behave that way. But the difference with an accretion disk is that it's not just flowing in a pipe in a straight line, it's rotating as well. And that rotation adds a huge degree of stabilization. So it turns out if you try and do that, it just doesn't work. It's interesting because this was a point that was controversial for a while, whether there would be on a purely hydrodynamic basis, that is to say just the ordinary fluid equations in a disk, whether there would be some kind of a more subtle mathematical process, a nonlinear or a subcritical instability as it's called, that would make the disk unstable. If it was, it would have to be pretty elusive because they never saw it and it never turned up in the simulations. So to get to what I actually did, there was one, it seems kind of a trivial thing that was left out. And that is in any astrophysical gas, and certainly in the gas surrounding black holes, there will be magnetic fields. And the magnetic fields, there was sort of a sense that, the late astronomer Ed Spiegel, the way he put it, also another fluid dynamicist at Columbia, he said it wasn't sporting to put in a magnetic field into the equations. That was because those were complicated. You could sort of get away with anything. And so there was kind of a psychological sense in which they were avoided. But it turns out, and this was the subtle point, I think, of the work, and that is that you could take the limit that the field went to zero, and not exactly zero, but much smaller than any other kind of dynamical variable. The magnetic pressure was much smaller than the gas pressure, all of that. So you could put in just a trace of a magnetic field, and it turned out that made rotational motion completely unstable. And the rate at which it broke down, the so-called linear growth rate, was independent of the strength of the magnetic field. And so the work that I did was sort of a detailed analysis of that process. And it could be understood very simply, provided you take a few things that I say, on faith. So here's what you have to take on faith. If you have a magnetized fluid, just if we could there is a magnet. If we could ionize the gas in the room and use the Earth's magnetic field and kind of pull the fluid particles apart, then the effect of the magnetic field would be like a tension, almost like a solid. You know, you could displace the fluid elements and they would vibrate back and forth. And now imagine that that occurs in a disk. The effect of a magnetic field is very much like you had two, imagine two orbiting masses, and they're connected by a weak spring. So that's the analogy that you should think of. And it's a very good analogy. The equations turn out to be exactly the same. So what would happen, just forget the magnetic field now, let's look at the masses on the spring problem. What would happen in that kind of a system? Well, if the spring is very, very strong, then it would be as though they were connected by a rigid rod almost, and they would just orbit together. But what about if the magnetic field is weak? Well, what would happen then is that the inner mass, being closer to the central source of gravity, the inner mass would be rotating faster, and the outer mass would be rotating more slowly. So the spring would tend to get elongated. So the spring pulls back on the inner mass, and it pulls forward on the outer mass. Now this is interesting because it's very counterintuitive. So you'd think if you're pulling back on something, it slows down. And normally that's what it would do if you were just walking, but not in a rotating system. So what happens is that it loses angular momentum. And it drops, so I'm speaking now of the inner mass. And so the inner mass loses angular momentum. It drops to a lower orbit, but lower orbits are going faster. On the other hand, the outer mass is being pulled forward. You think it speeds up? No. Its angular momentum increases, but then it moves it spirals out, it moves to a higher orbit, and its velocity actually slows down. And now the inner mass is moving faster relative to the outer mass, and so the process continues and it runs away. And that's the physical explanation for why a magnetic field is so destabilizing. And the people when the theorists like to measure a growth rate, how quickly does, say, the separation between two fluid elements who are tethered like this, how quickly does it double, roughly speaking? And the answer is that it's only a fraction of an orbital time. So very, very quickly, you have fluid elements moving in, you have fluid elements moving out, and then they are colliding with each other and mixing. And so it is turns out to be a very simple instability to simulate on a computer, at least to see the process itself. To figure out what ultimately happens in the turbulent fluid, that's a difficult problem to do because turbulence is still not something that we can do very easily, even numerically. But at least it gets you started. So that was the work that I won the prize for, and my colleague John Hawley. So I was the theorist, I did the pencil and paper bit, and then John was the one who did the heavy lifting, and so he did the first numerical simulations which showed a perfectly, laminar flow, as we say, break down into turbulence, and showed that, in fact, the instability would work as advertised.
Amazing.
So that's why I won the Shaw Prize.
That
was a long-standing problem. That had been a problem that, when we did our work, had been around for, I think about 25 years or so.
No, I was going to say, I really enjoyed the way you explained it. It felt like I was in an Oxford tutorial.
Oh, very good. Well,
which I mean in a very complimentary way.
I understand.
And I do want to talk a little bit about Oxford, because obviously that is our link. We apparently have offices very close to one another, which we have recently discovered, being in neighbouring colleges. So your position there is the Savilian Professor of Astronomy.
Yes.
And I had to think carefully about what I was saying.
Astrophysics or astronomy, yeah.
Sorry.
Yeah. No, you're right.
It is astronomy.
It is astronomy, but people get confused. Yeah.
Right, okay. Because I was getting confused because I am also aware, I guess, as a mathematician,
yes,
or at least there's the Savilian Professor of Geometry.
My dual.
Yes. Yeah. So I had heard of these positions, but I never actually looked into where they had come from.
Well, actually, I should put in a plug. The individual who was the Savilian Professor of Geometry when I arrived at Oxford, Nigel Hitchens, is also a Shaw Prize winner for his work in geometry.
Brilliant.
So we've got it covered at New College.
Yeah. So if you want to win a Shaw Prize, become a Savilian Professor, and apparently it's a given.
Comes with the territory.
Yeah. No, I was going to say the history I found fascinating, and this idea that these positions were created over 400 years ago to further the education and study of mathematics.
Yes. Trigonometry in particular.
Yes.
That was the one they were, apparently Saville was not happy with the state of knowledge of trigonometry among the undergraduates.
Yeah.
And of course, astronomy at the time was very positional. And being on the surface of a sphere, spherical trigonometry was, if you've ever actually worked with those, they're not simple equations. No. So they were, but that was the kind of discipline that had to be mastered if you wanted to be a successful astronomer in 1619 when the chair was created.
Yeah, and it did mention tuition of trigonometry. There was a requirement to have studied the philosophy of Aristotle and Plato.
That's right.
Which I found was just quite entertaining.
I think the word they used was imbibe the philosophy.
Yes, you're right. And the other thing that sort of jumped out at me around that was the requirement to give 2 weekly lectures.
Yes.
Or to be fined a significant proportion of your stipend.
And I think you were not allowed to cast horoscopes.
Yes.
That was discouraged.
Yes. So I was...
That was tempting, but I had to relent when I accepted the position.
But I just found the whole thing, as I say, I found it fascinating, but really interesting that astronomy was seen as very much a part of mathematics.
Yes.
In that time period. Whereas now, perhaps, again, I found it interesting to hear the way that you were describing the importance of the mathematics in the work that you do.
Yes.
But yet, I think there's still kind of almost like a separation, at least to some people, between astrophysics, astronomy, and mathematics. But yet...
They've certainly grown a little bit more distant. Depending upon exactly what you do, there are some... Nowadays, there's a whole new kind of field of mathematics which involves data reduction techniques. When you have massive amounts, that's true in a lot of fields, but especially astronomy, there's a huge data glut. And so it's interesting because a lot of, there are big portions of the field that are really into these sort of techniques now, particularly cosmology is going to have a lot of instrumentation now. We're going to hopefully we will learn a huge amount about the universe, but we have to be clever in terms of how we extract the information from these kinds of data sets.
Yeah. So I guess the point I was trying to build to was, did you come into this field through a passion for mathematics, a passion for physics, a passion for astronomy? How did you end up doing astrofluid dynamics?
So when I was a little kid, I always had an interest in astronomy. And my father was a physician and some training in science, but he also was one of these people who he would remember we had things called newspapers, and they were printed on paper, and there would be a monthly astronomy column in our local paper in Philadelphia where I grew up. And he would cut it out, and it was called The Sky at Night. And he was one of these people who just loved to identify bright stars and constellations and always be aware of when the meteor showers were occurring and so on. And so, I would gaze at the night sky with him. And so I can remember one of my earliest memories are learning about Orion's belt and the constellation. And so it was interesting when I came back later and had a more sophisticated understanding to go back to that. So I was always interested in astronomy from that point of view. But as a student, it wasn't something that I was particularly gripped with. either in high school or in university. I was much more interested in mathematics.
Right. Yeah.
And so I was a very keen mathematics student when I was in high school. And my senior year, I was even excused from classes. I could just, read the books I wanted to read and study, and I went to MIT. And I started off, as a mathematics major.
Yep.
And then the more I understood about it, the more I realized that the aspects of mathematics that I like were problem solving. Mm-hmm. And so I was attracted to theoretical physics because there the mathematics is used as a means to an end, not just as an end to itself. Mm-hmm. And so I double majored as an undergraduate in both mathematics and physics. And I went to graduate school in Berkeley because it had a very good physics department in all disciplines. And there I met a theoretical astrophysicist, Chris McKee, who became my PhD advisor. And I realized that I could sort of work in a discipline which combined my three sort of principal interests. So I came to the subject sort of along the lines, I hesitate to compare myself to a giant, but just by sort of analogy to somebody like Chandra Sekhar, who I think was really, he was considered, a theoretical astrophysicist, but he has many books which are really on, among other things, the stability of fluids, and a classic book on black holes. And he approached the subject from a very mathematical point of view. And so I'm a little bit from that direction. I'd like to think that I'm a little closer to the physics, and I'm not afraid to kind of fuzz over the mathematics if I can get a physical insight by being a little, I don't want to say careless, but without obsessing over rigor.
Yeah, you're speaking to, I completely agree. Sometimes it's interesting because I teach a whole range of courses, both very, very pure and very applied, but as an applied mathematician, fluid dynamics, I do often get my students sometimes being like, but is that really rigorous? And I'm like, oh, don't worry about it. It's, we're just trying to...
You can do the rigor later.
Yeah, you can.
You can go back and fix it up if it turns out that what you're working on is really fruitful.
Yes.
And that's, I try to bring that kind of philosophy to the problem.
Feel free to talk more if you wish on the answer, but these are ones that if you want to just give a one-word answer is totally chill.
Okay.
Kind of, you don't need to necessarily explain the answers. Okay, so first one, do you prefer blackboards or whiteboards?
Oh, blackboards, no question.
Yeah.
Whiteboards are a bane to the human species. Next question.
Good answer. Pi or tau?
Pi or tau? I'm not sure I understand the question.
So there is you're not the first person to say this, because I only recently discovered this. There's a group of vocal mathematician scientists who believe that we should define things through 2pi, aka tau, rather than pi. It's just sort of arguing that it makes more sense that things are measured as 2pi as the distance around the unit circle instead of pi.
Oh, no, pi comes up too much just by itself. I'm a pi guy.
Yeah, I agree. Degrees or radians?
Oh, radians, yeah.
Okay. Do you have a favorite number?
23.
Okay.
I don't know why. Well, I do know why. But somehow when I was a kid, my birthday is November 23rd.
Right.
And so I was thinking that, gosh, there'll be, in 1976, I'll be 23 years old on November 23rd. And somehow the mathematics of that just seemed fascinating to me. And plus 23 was so old, So somehow that's always, I notice 23 if I happen to see it. Like this is 2023 and the month is November 2023. So I'm always, when I see signs like this, it's just sort of an emotional thing. So that's, if I had a favorite number, that would have to be it.
Is there a particular equation or mathematical result that you find delightful or beautiful or elegant? Just,
Yes, I think at the simple level, the Euler's formula, e to the I pi plus 1 equals 0, but that's sort of everyone's favorite, and that really is an amazing theorem. On a more sophisticated level, that's sort of the Cauchy equation, which in complex variables, where you define a function as an integral over the function itself, and then a z minus zeta in the denominator. And something that it's so simple and easy to prove, and then what follows from that is just astonishing. In 30 seconds, you have the fundamental theorem of algebra, and you haven't done anything, it seems like. So that has always, the power of complex variables has been something which I have just been in awe of since I first studied them as an undergraduate.
Yeah, I teach complex analysis for second years, and I have, now that you mentioned it, I have the residue theorem.
There we go.
Tattooed here.
Yeah.
It's not quite Cauchy's theorem, but very similar.
Exactly, exactly. Oh, very good.
So,
you're even more dedicated than I am. More of a fan. Yeah.
And last one, do you have a favorite star or planet? Or celestial body, shall we say? Let's keep it.
Well, again, I think I would probably, I don't have a very sophisticated reason for it, mostly just sort of childhood memories. It would be the earliest constellations that I learned with my father. So I would say my favorite constellation is Orion, because it's so clear and so obvious. And then it turns out that, and then a favorite star, like Betelgeuse. Now that's gotten a lot of notoriety, but it was one of the early stars that I learned. It definitely does look red when you look at it. And then as an astronomer, I could understand why it's red, and it's going through its red giant phase. So there's another level that I can appreciate it. And it's also the region in the sort of nebula in Orion's belt is the region in the galaxy, the nearest region in the galaxy where star formation is occurring. So there's sort of a lot of memories in that, and a lot of astrophysics as well. So for me personally, Orion would be my favorite constellation.
Awesome.
It's not a question I get asked very much, but it's fun to sort of think about it. Yeah.
Awesome. Well, Steven, thank you so much. That was
a real pleasure.
It was a lot of fun. I thoroughly enjoyed it.
As did I. Yeah.
Good. Perfect. Right. That's what we like to hear. And so thank you, Steven, again. Thank you to all of you for watching. If you have enjoyed this, please do remember to subscribe. It's really helpful. And I'll see you all soon with some more maths fun. Take care.